Anything in, anything out. True to this concept, the FA-1616 series flexibly supports a wide variety of inputs and outputs and is being utilized in a broad range of system configurations. Supporting this anything in, anything out concept are its diverse interfaces and high scalability through software-defined architecture.
First, let's look at the range of interfaces. The FA-1616 supports various signals used in broadcast and video production, including SDI, IP, Dante, and MADI. Since it can handle mixed SDI and IP environments in a single unit, you can gradually migrate to IP-based workflows while still making the most of your existing SDI equipment. By combining options, it can also serve as a gateway connecting IP and SDI.
Next, regarding its software-defined nature, the FA-1616 allows you to switch its internal processor configuration via software. You can select and configure necessary functions based on your application, such as up, down, and cross conversion, SDR and HDR conversion, and color conversion using 3D LUTs. As a result, there is no need to replace hardware even if your operation changes, allowing you to use a single unit for a long time to suit your needs.
The FA-1616 features a lineup of 3 models. From 3G SDI to 12G SDI environments, you can select the right model to match your system configuration and operational scale. Operational flexibility is another hallmark of the FA-1616. Unit settings and configurations can be managed from a PC via a web browser. Furthermore, it supports dedicated remote control panels, allowing for physical button operation.
2 years since its release, the FA-1616 continues to leverage these features to support operations in various professional fields. Today, we would like to introduce the new features added to the FA-1616 since its launch.
There have been many updates, but we will focus on 7 features today. Let's start with the Event Save Load function. The configuration saving capabilities of the FA-1616 unit have been enhanced. There are now 3 patterns available for saving unit settings.
The first is Event Save and Load. The second is Backup and Restore. And the third is the Export and Import function for network settings. With Event Save Load, you can save multiple FA-1616 unit settings as events. Recalling a saved event reflects the settings on the unit immediately. These events can be imported or exported as CSV files, enabling quick configuration changes across multiple FA-1616 units. Additionally, you can generate event data using Excel. The event data generation tool can be downloaded from the FA-1616 unit itself or from our website. You can create event data using an Excel file like this. By generating only the necessary sections here, you can shorten the event loading time. Now, let's demonstrate. Clicking the button in this cell allows you to use the filter function. As you can see, the items match those found in the FA-1616 web GUI. By selecting each item one by one, you can display only the sections you wish to configure. Referencing the values in the Setting Range column, you can change the values in the Setting Input column. As we modify the settings for each item, an asterisk appears in the Changed Items column. Once you've finished changing the values, you can easily export the data for these modifications to a CSV file. Then, import this data into the FA-1616. Select the Event Import and Export tab under Utility in the Web GUI. Select the CSV file you just exported using Select File. Next, from the Event Load and Save tab, load the imported event. You can see that the values set earlier are now reflected. Additionally, saved events can also be loaded via GPI.
The Backup and Restore function allows you to save and load all FA-1616 settings, including network functions that aren't covered by saving an event. The Network Setting Export and Import function allows you to save only network-related settings to a PC or write saved data back to the unit.
In this way, you can save or update the unit settings depending on your specific requirements. Now, let's explain the JPEG XS support. We have introduced an encoder-decoder option for the JPEG XS ST2110-22 compression codec. Key features of JPEG XS include its ability to reproduce image quality comparable to uncompressed video while using network bandwidth efficiently through compressed transmission. Please take a look at the video compressed with JPEG XS on the FA-1616 compared to the original video. We have used a compression ratio of approximately 1.7 here. There is almost no difference in image quality from the original, and there is no latency. Furthermore, looking at the data usage, a video transmission that would normally require about 1.5 gigabits per second has been reduced to 195 megabits per second. JPEG XS is a standard for broadcast and professional video specifically designed to transmit high-quality video with low latency and high efficiency. This is how we can reduce data volume while maintaining image quality. Since the bandwidth required for video transmission is reduced, it helps lower communication costs for international event broadcasting and interstation transmission. Video latency is now represented visually. To make latency adjustment easier, we've updated the Web GUI to display video latency visually. You can check the video phase status relative to the reference signal on a screen similar to a waveform monitor. Additionally, you can numerically verify the internal processing latency on the same GUI screen. Let's look at a demonstration of actual latency adjustment. You can check the latency and phase of the FA-1616 by accessing the Synchronizer Adjust Timing block on the home screen or the corresponding item in the left-hand menu. First, let me explain the default settings. By default, a total delay of 2 frames occurs, combining sync delay and IP delay. This delay amount is preset with a margin to ensure stable operation in any operational environment. Sync delay is the latency generated during synchronization processing. To support various input signals, including asynchronous signals, the setting is based on the assumption of a frame delay.
On the other hand, IP delay is the time from receiving an IP stream until the decapsulated signal is input to the synchronizer block. The initial value for the hitless buffer is set to 10 milliseconds to ensure reliable reception even when network latency or the delay difference between path A and path B, is large. Combining this setting with the default for PTP alignment point output and the playout timing set to 0 line results in approximately 1 frame of latency. From here, we will show you how to reduce this latency.
First is the IP side configuration. Open the IP receiver screen and configure the Adjust Timing items. In environments where network latency or the delay difference between path A and path B is not that large, you can shorten the time packets stay in the buffer by setting the hitless buffer value lower than the default 10 milliseconds. In this example, we set the hitless buffer to 0.1 milliseconds. The default playout timing is set so that the decapsulated signal phase matches the PTP alignment point, the 0H timing. By adjusting the playout timing to match the timing when the signal is read from the hitless buffer, 0.1 milliseconds in this case, we can output the decapsulated signal with low latency. Since the hitless buffer is 0.1 milliseconds here, we set the playout timing to 9 lines, approximately 0.3 milliseconds. This configuration confirms that the IP side latency has been reduced.
Next, we will configure the sync delay side. On the GUI, the output phase timing is shown as a solid pink circle, and the input signal phase relative to that output phase is shown as an orange ring. At the same time, the input signal phase values are displayed on the right side of the screen. In this demo, you can see that the input signal is delayed by 263 clocks in the H direction and 9 lines in the V direction relative to the output phase. These phase differences can be adjusted by operating the H/V timing bars. First, the H direction output phase is adjusted using the H timing bar. Here, as an example of H timing in action, we are moving the output phase to overlap with the input phase.
Next is the V direction output phase. While this can be adjusted with the V timing bar, in this demo, it falls outside the phase pull-in range for frame mode, meaning it is not at least 2 lines advanced relative to the output phase, resulting in a frame delay. Therefore, we adjust the V timing to delay the output side phase, so it falls within the pull-in range. By setting the V timing to 12 lines, we adjust it to a state with no frame delay. Because you can adjust while visually confirming the phase, latency optimization can be done intuitively. Ultimately, the total latency, which was in milliseconds initially, has been reduced to microseconds, minimizing the delay. Next, let me introduce the timecode generator function. You can embed input side timecode, LTC or ATC, or timecode generated within the FA-1616 unit into the output signal. Furthermore, if there is a difference in latency due to different paths prior to the FA-1616, an offset of plus or minus 15 frames can be applied to the input timecode. Since the timecode generated by the FA-1616 can be output as LTC, it can also be used as a timecode generator for multi-system recording at events. Regarding ST2110 one-to-many support, this function copies a single input stream to multiple receive streams within an SFP port, SFP A, B. Even if you want to receive a specific stream with multiple receivers within the same SFP port, typically only one stream's worth is sent from the IP switch. However, by using this function, the FA-1616 can distribute it to each receiver internally. Next is the packet FS support. On the IP receive side,
A new Packet FS mode has been added that buffers and decapsulates without referencing the RTP timestamps within the packets. Since it doesn't use timestamps, video can be received even if it isn't locked to PTP, depending on the sender equipment's environment. For example, for high latency streams, such as international event feeds that cannot be handled by hitless buffer adjustment alone, reception becomes possible by using Packet FS mode.
Regarding in-band control support, NMOS control has been enhanced. In addition to out-of-band control, in-band control is now supported. While out-of-band control requires separate networks for media and control systems, in-band control allows both systems to operate on the same network interface. In addition to these, the FA-1616 has continued to evolve with many added functions to better suit our customers' operations. In the future, we also plan to introduce a gateway model with reduced pricing. For more information about the FA-1616, please feel free to contact your local sales representative.